Hi, thank you for your interest in our work on machine learning, explainability, and fairness, insights from consumer lending, recent research from FinRegLab led by PR Stark and professors Laura Blattner and Yazdi at the Stanford Graduate School of Business. This workshop presents a portion of the results from a broader study of the explainability and fairness of machine learning for credit underwriting. It focuses on whether we have the tools to make machine learning models fair under current anti-discrimination requirements. Our work evaluates certain model diagnostic tools currently in use in the finance services that are designed to help lenders understand and manage ML underwriting models. Participants include 7 financial technology companies who create products for lenders and other AI model clients to understand, explain, and manage those models. We evaluate whether these tools help make machine learning underwriting models sufficiently transparent to be used in a high-stakes environment such as consumer lending. For more detailed information about our study, you can find our full report at finreglab.org. For this workshop, we highlight our work investigating the question of why some groups are treated differently by models, which aligns with the general framework of fair lending laws and specifically disparate impact management. We focus here on the results pertaining to usability, that is the ability of a tool to identify less discriminatory alternative models, a key component of fair lending requirements. 4 of the 7 companies participated in the usability section. This graphic shows a rough layout of our process. We provided 3 data sets, training, testing, and deployment testing. The models used for the study include logistic regression, simple and complex neural nets, and XGBoost models. We focus our analysis on the logistic regression and XGBoost models since we received the most complete result for those models. Our evaluation process included several stages. The research team and companies trained their models on the training data set and provided their corresponding predictions of default on a testing data set. Participants then provided recommendations on how to create less discriminatory alternative models through various methods of their choosing, from feature dropping using information from explainability tools such as SHAP, Lyman permutation importance, to reweighing training data to give less weight to observations in the disadvantaged group that default, to using automated tools that search for a range of less discriminatory alternative models. We evaluated whether the less discriminatory alternative models proposed by each participating company reduce adverse impact when test data are run through the models, and at what cost to predictive performance. Finally, companies generated less discriminatory alternative improvements using a deployment test data set with a different applicant composition. This last test allowed us to assess how well tools generalize to a different environment. For this presentation, we'll look at the results for the XGBoost test data set. All companies were provided with a baseline XGBoost model trained by the research team. We characterized the models with various metrics, but we'll focus on 2 for the following analysis. AUC here is the value measuring the predictive accuracy of the model, and AIR is the adverse impact ratio, which measures disparity as a ratio of the minority approval rate over the majority approval rate, where an AIR closer to 1 represents a fairer model and is used as a measure of model fairness in industry. The metrics for the baseline XGBoost model are 0.87 AUC and 0.73 AIR. 2 companies chose to modify the baseline model we provided them with, and therefore started at slightly different baseline than the rest of the participants, as you'll see in the following plot. The baseline values from the previous slide correspond to the point at the top left of this graph and overlaps with some of the less discriminatory alternative results. And the other 2 baseline points are colored in blue. The companies used a variety of proprietary methods to identify less discriminatory alternative models, which we see plotted here. Anonymized is various methods. So a method is a company's chosen process to reach a less discriminatory alternative. 3 methods used automated tools represented by the solid line, the dotted line, and the X symbols, such as joint optimization techniques. And 3 methods used versions of feature dropping, the circle, the square, and the diamond. On the y-axis, we have predictive performance, where higher AUC means the model performed more accurate predictions. On the x-axis, we plot adverse impact ratio, again, where an AIR closer to 1 represents a fairer model. Ideally, the best less discriminatory alternative model would be in the upper right corner of this plot, where high predictive performance and high fairness. We see from this plot that the feature dropping methods do not improve in fairness, but even come at a cost of predictive performance, which is shown in the diamond. However, the automated methods sketch out an efficient frontier of the models that feature different disparity and performance metrics. Our results showed that the ability to describe features that drive disparities with respect to a protective class does not automatically lead to models that are less discriminatory alternatives when this information is used mechanically. In other words, automated tools perform significantly better than strategies based on dropping features that were identified as drivers of disparities in the model. While we showed only the results for the XGBoost, these results can be generalized to all model types, such as neural net, logistic regression, and proprietary company models. For more detailed information about our study, you can find our full report at finreglab.org. Thank you.